This is the second video in our introduction to interferometry. And in this video, we are basically going to learn a little bit more about the algebra, which is behind beamforming. And the endpoint for this video is for us to show that beamforming essentially is a Fourier transforming operation. And that basic insight is very important because it is at the heart of how radio interferometers form images of the sky. So let's again start with our basic example where for simplicity, we have just taken a one-dimensional array of antennas which have to be beamformed. And so all of these antennas are arrayed along the x-axis at positions given by x equal to d of I, where I goes from 0 to n minus 1. So there are n such antennas arrayed along the x-axis. Now let's suppose that there is only one source in the sky at a zenith angle theta, like we had considered before. Now the electric field of that source on antenna I is going to be given by this expression where E naught only depends on how bright the source is. And then this complex exponential here is denoting the path length which the source has to, or the waves from the source have to travel to reach different antennas. So for I've taken the reference level here at x equal to 0. So that's the reference phase. The exact location of the reference doesn't really matter, as you'll see later. What really matters is the differential path length that the wavefronts have to travel to reach different antennas. So in this case, the extra path length to antenna I has been converted to a phase for a monochromatic wave, and that phase is given by this expression. Okay, so what do we really do in beamforming? What we do in beamforming is essentially written over here. We take the electric field of each antenna, we multiply it by a complex weight, which I'll explain soon. And then we sum all of these values, and then we take the absolute value square to get the power. These complex weights are exactly designed to cancel out this extra path length induced phase, which the wave has when it reaches antenna I. So obviously that complex phasor is just going to be the conjugate of this. So it'll just be the same expression, but with a flipped sign. So there's minus here, it'll be plus here. And beamforming again is basically this expression, and it's an absolute value square of a complex quantity. So I can always write it as that quantity multiplied by its own complex conjugate, which I've written here. So now I get a double summation where I and k both run from 0 to n minus 1, EI, EK conjugate, and the complex phasors WI and WK conjugate. Now, if I again write down the actual expression for EI and EK based on what the electric field is at the location of the antennas I and K, I get something like this. I get this double summation. And now with the beamforming phasors or beamforming weights, which I have to apply. Now, if I adopt the correct beamforming weights, which is just given by this expression here, then I get something like this, where these two exactly cancel each other out. That's not a surprise. That is the intention of beamforming. And then E naught square, the absolute value square, is basically just the brightness of the source. You know, a brighter source will have a higher value of E naught square. And so the beamforming operation will just give me E naught square times n square. So n square is the number of IK pairs, and these two cancel to give unity. Okay, so that's the basic idea of beamforming. Now, to take this idea a little further, let us now suppose that you beamformed in the wrong direction. Okay, so let us suppose that there's only one source in the universe, and that is at direction theta. But for some reason, you decided to beamform in the direction phi. So what's going to happen? So here, the output of the beamforming operation is given in this expression. So this part of the expression remains unchanged. E naught square, that's the brightness of the source, remains unchanged. But now the complex weights which you apply during beamforming have changed because now they have an angle phi instead of the angle which had to be theta. So you get something like this. Now, notice that this is basically a summation of a lot of different exponents with with different angles. And the range of angles depend on how big the values di minus dk are, and how big this difference is. Okay. Um, Now, if these values are sufficiently large, then you're going to get addition of a lot of different complex numbers with completely random arguments. And the arguments can go from 0 to 2 pi. And if they do, then all of this will sum to a value very close to 0. You're just, if you want to imagine this in the complex domain, in the two-dimensional complex plane, you're just adding vectors which all have different orientations, so they all cancel out. Whereas before, when we had the correct weights, all of these were just like the number 1. They were just unity, so they all summed coherently. Now here they are all summing incoherently, which means they're all going to average down to a very small value. So let's see when this will average down to a value very close to 0. For this to average down very close to 0, the angle which enters the complex exponent, the range of those angles should be larger than 2 pi. That's when you get a truly random averaging of all the complex vectors. So let's see what that looks like. So omega by c, so omega is the angular frequency, c is the speed of light, times the baselines, delta d, which encapsulates the baseline lengths, times a delta of sine theta, right? That's what we have here. Now, if that value roughly is greater than 2 pi, then all of this will average to 0. Now, omega by c, if I bring 2 pi to the other side, that just gives me 1 over the wavelength, lambda, and delta d is the delta d remains the same, so delta sine theta greater than 1. So that's when delta sine theta is greater than lambda over delta d. Okay, so lambda is the wavelength of light, delta d is the distribution of baselines. This averaging will be the most effective when the baseline when I include the biggest baseline lengths that I can fathom in the array, right? And so that's roughly equal to the size of the array. So whenever you have an array whose total dimension is larger than lambda by d, then you're going to have complete decoherence or incoherent averaging over an angle given by delta sine theta. So if you remember, this is very similar expression to what we said was the angular resolving power of an aperture. And this is basically a rough derivation of what the angular resolving power is. So that's the basic insight you get just from incoherent averaging of these phasors in beamforming. So the final result we have is if you beamform in the direction of the source, then you have full sensitivity to the brightness of the source. If you beamform away from it, how much away from it is given by this expression, then you have very minimal sensitivity to that source. Okay, so that's the essential idea behind beamforming. Okay, now let's suppose that we don't have a single source on the sky, but we have a collection of sources on the sky. And so now we want to make an image of the sky. Again, we are working in 1 dimension, so image here should be taken as a 1-dimensional image. We'll get to generalizing it to a 2-dimensional sky later in later lectures. So let's suppose we want to make an image of the sky. We have just learned that when you beamform in direction theta, you have maximum response to sources in that direction, and you have very little response or close to 0 response in directions which are much different than theta. Okay, and how much is much different? Of course, that angle has to be greater than lambda over d. Only then your response falls to 0, but in any or close to 0. In any case, if we want to make an image of the sky, then we are looking for solving for a function which is I of theta, so intensity in direction theta. Okay, so now there's one more fundamental insight here, which is that this whole expression must only depend, the whole expression inside the summation must only depend on the baseline, di minus dk, and not on the absolute location of any antenna. And that just comes from the fact that all of the astronomical sources are really far away there. You can almost think of them as they're at infinity. which means that it does not matter where on the earth you're going to build this baseline, you will measure the same image of the sky. And that is just to say that no matter the absolute location on the earth or where you're building this interferometer doesn't matter. All that matters is the relative location of the different elements of the interferometer. So all of these, the entire summand inside here, the expression should only depend on the baseline vector di minus dk and not on the absolute locations of absolute locations of these antennas on the earth. So I can now convert this, or at least notationally, I can write this double summation as a summation over all possible pairs of antennas, so all possible baselines, times this EI-EK conjugate is basically the two-point complex correlation of the electric field on the ground. And that again should not depend on the absolute location on the ground. It should only depend on the distance or displacement between I and K. So that can be written as a function called the visibility. And that visibility only depends on the baseline. It doesn't depend on the absolute location on the ground. And again, of course, this complex phasor only depends on di minus dk. Okay, so that's the basic insight which we need to go from this expression to here, which is just realizing that it's only the baseline lengths that matter, not the exact or absolute location on the earth which matters. Okay, and then we are now done. So if you look at this expression where you have a summation over all baselines of the two-point correlation of the electric field, which we are going to call the visibility, multiplied by this phasor, which basically originates from the beamforming weights which you have to apply. If you look at this expression, it basically is a Fourier transform expression. So you have a Fourier transform to go from the visibility to the image on the sky. Okay, so in this Fourier transform, what are the Fourier conjugates? The Fourier conjugates are the baseline in units of lambda or the wavelength. Okay, so lambda again comes from writing the angular frequency divided by c in terms of, you just write omega by c as 2 pi by lambda. So this is the baseline in units of wavelength. In the same way, we have that baseline in units of lambda and angle on the sky are Fourier conjugate variables. And that's it. That's basically where our essential insight in interferometry comes from. So in interferometry, all you have to do is measure this visibility function as well as you can, and then basically take a Fourier transform, and then you'll get an image of the sky. And that's the basic insight of interferometry.